Okay, so welcome back to the next session, and in this session, we are going to see the mass luminosity relation, the period density relation, Virial theorem, and some problems based on these relations. So, Professor Glassell has already summarized the stellar structure equations, so my task is fairly easy to show you only the equations, and we can derive the relation between mass and luminosity for stars. So I will start with these equations to give you an idea. In the Eulerian form, we write the mass conservation equation here. This is dm by dr is equal to 4 pi r square rho, and the hydrostatic equilibrium is basically the pressure gradient dp by dr, which is equal to minus g mr. Mr is the mass enclosed in the radius r, divided by r square multiplied by the density. The third equation, that is the energy transport equation. This equation is written under the assumption that the energy is being transported mainly or mostly or purely from the radiation, and we have assumed the diffusion approximation. So under the diffusion approximation, we write the temperature gradient in this form here, minus 3 kappa rho divided by 4 AC T cube L divided by 4 pi r square. So here you see kappa is representing the opacity, A is the radiation constant, C is the speed of light, rho is the density, T is the temperature, L is the luminosity, and R is the considered radius. Now, for the sake of completeness, I would also like to mention the energy conservation equation. So this is dl by dr. This is equal to 4 pi r square rho and then epsilon. Epsilon is actually here is representing the coefficient of energy generation rate, and in this coefficient obviously we are not specifying at the moment, but it is also including the kappa epsilon nu epsilon due to the epsilon, which is also including the nuclear processes plus the thermodynamics as well as any kind of energy loss. For example, if the neutrino is leaving the system, that is also included in this epsilon. So now, in order to derive the mass luminosity relation for the stars, we simply assume that, let's say that the star is in a hydrostatic equilibrium. So we write the pressure gradient, and the pressure gradient is written here. In an approximate way, we write the hydrostatic equilibrium here, for example, dp by dr in terms of p by r, and this is proportional to mass, rho, and r square. Obviously, the capital G is the universal constant, so you can forget about, in order to find out the relation between these two quantities. Now, you see here, the density rho can be represented here, mass divided by r cube. So you have basically mass rho divided by r square. So here 1 r is going to cancel this one. So simply you can see this P in the pressure will be proportional to m divided by r, and then you have this term m divided by r cube, which is coming from the density. Now, in a compact form, this expression can be written as P proportional to m square divided by r to the power 4. Okay, is it fine to all of you? You are able to follow the relation? Okay, perfect. So I request all of you also try by yourself, so that if you have any issue, we can immediately discuss. Now, let's park this relation here and call it as a relation A. And now we see the energy transport equation purely in the case of radiation under the diffusion approximation. We can write in the Eulerian form. We can write the diffusion. We can write the energy transport equation dt by dr. The temperature gradient is equal to minus 3. Again, these terms, kappa representing the opacity, rho is the density, 4 AC is our constant, and T cube, and then we have a factor L multiplied by 4 pi r square. So we can write after dropping all the constant here, we can write this expression in terms of T by R will be proportional to rho into L, which is the luminosity, divided by T cube multiplied by r square. Okay, so we are dropping out, for example, 4ac term, and we are neglecting at the moment the dependence on opacity. So it means that from the energy transport equation we can write T divided by R is proportional to rho into L divided by T cube and R square. From here you can write T is proportional, or T is proportional to rho into L divided by T cube R. So basically one R which is appearing here will cancel the other one and you are only left with one. Okay. Mouse is there. Yeah. If you write T here, you see here obviously T is proportional to rho into L divided by T cube R, and if you write this entire expression in terms of L, so you have this T here, T cube here, so this T and T cube will become T to the power 4, and then you have here R cube. If you convert this rho into M divided by R cube, obviously the density is nothing but mass divided by the volume, and volume is being represented by R cube. So in this case, this rho will become M divided by R cube, and you have this L expression for T, this T cube multiplied by R cube and R. So ultimately what is going to happen, luminosity will be proportional to T to the power 4 R to the power 4 divided by mass M. Are you able to follow the relation, right? Let's park this relation here and we call this relation as a relation number B or relation B. Now, if assume that the material of the star is made up of ideal gas, in this case the pressure will be actually proportional to the density times the temperature. So it means P here is proportional to rho into T, and if you write rho in terms of mass and radius, so P will be proportional to mass divided by R cube multiplied by T. Okay. Now if you simply look back the relation A, this is what we had. P, pressure P is proportional to M square by R4, and here we have P proportional to M by R cube T. This case you can write by comparing these two equations with these two relations in terms of right hand side of these two relations. So eventually it will lead to the formation of a relation between M, R and T. So this M square divided by R square, R to the power 4 not square, proportional to M divided by R cube multiplied by T. Let me show you once again what we had here. This one what you have here, pressure P is proportional to M square divided by R to the power 4. Remember it is coming from the hydrostatic equilibrium relation, and now here what you had is P is proportional to mass divided by R cube multiplied by T. Okay. If you compare these two relations, eventually you will get relation between mass, radius and the temperature. Okay, this is the way we can get rid of pressure, because our target is to find out the relation between the luminosity and the mass. Okay, so we are just trying to eliminate other quantities which are there, and pressure was one of the quantity we wanted to get rid of it. Now if you simplify this, so obviously what is going to happen, you see you have R to the power 4, we have R to the power 3, this will lead to only one R, and this we have M square and this M. So eventually you have T which is proportional to M divided by R. Let's say this is a relation C. So now we have a relation between T, M and R. Now look back the equation relation B. What we had, this relation B is actually luminosity, relation between luminosity, temperature, radius and mass, and now you have a relation between temperature, mass and the radius. What should we do? to get rid of temperature? Exactly. So what you can do, just take this relation, because you want to get rid of T from that expression. So you just take this relation and put it in the relation B. Take a look here. So you substitute T in terms of M and R. So this T, we would like to have a relation between L and M, and T is coming to the picture. So just let's put the value of T and the relation T there and see whether R is still appearing or we get rid of R. So what you are getting if you are doing that? M cube, all of you are getting M cube? Okay, perfect. Yeah, this is what I am also getting. Now, what this relation is telling, can you comment? Anybody have thought about it? So we have a relation between luminosity and mass, and what we have used in order to derive this relation, what equations we have used? Hydrostatic equilibrium, energy transport under the assumption that energy is being transported by radiation, and anything else? Obviously, we also have considered the pressure dependency on temperature and the density, but mainly considering the hydrostatic equilibrium and energy transport, you have a relation between mass and the luminosity. So what does that mean? If you write, let's say L is proportional to M cube, okay, if I have a relation, I can also write we have this L is equal to M cube, okay, so I can also write, assuming other thing is constant, obviously constant, maybe let's say A M cube. What we can interpret from this equation or maybe this relation, it's better to write this relation, but yeah, even if you want to try to make sense using the equation, tell me what is the significance of this equation or expression or relation. Yes. Yes, yeah, you're in the right direction. Obviously, luminosity depends upon the mass. That is already there, but what does that mean? I mean, yes, it is obvious that you increase the mass, luminosity is going to increase. That is there from the relation. But what is special about this relation? Maybe the master students or PhD students can help us. So if I want to use a value for M, what is going to happen for L? So this expression is actually telling us that if you tell me what is the mass of the star, then the luminosity of the star is being fixed by the mass, right? So it means you specify what is the mass of the star, then the luminosity of the star is being luminosity of the star is being fixed by the mass of the star. Okay. Then so now mass is a kind of very important parameter in stellar astrophysics. Okay. So if you specify the mass of the star, let's say we have a 7 solar mass, 8 solar mass, 10 solar mass of the star, then for that configuration you have a luminosity. Now the nuclear reactions inside the star, they have to adjust in such a way that the star maintains the luminosity, which is a kind of requirement from this relation that for a given mass, the star should have that luminosity. Okay, so it means for a given mass, this relation is telling us that for a particular mass, particularly this is more strictly valid close to the main sequence. and the relation, the value of this exponent 3 will differ. Maybe sometimes it will become 2.7, sometimes it will become 3.7 or 3.5, depending upon where you are. But this relation that L is proportional to m cube is mostly valid in the vicinity of main sequence. But the point is that only by considering the hydrostatic configuration and energy transport in the star, we have this relation. We did not even, we did not even talk about what is the energy generation process, or how the energy inside the star is being generated. It is only considering the hydrostatic configuration and then the energy transportation. Okay, only these two ideas is basically leading to the relation between mass and the luminosity of the star. And if you think in that way, mass is being fixed, luminosity of the star is being fixed by considering a particular mass. Okay, is it clear to all of you? It's fine. Professor Classel, any comment on that? Okay. Yes, this was what I was talking about. The luminosity of the star is actually being fixed by its mass, and this relation is kind of strictly not, I would say it's not universal relation, but it is like the exponent value of exponent may vary depending upon where you are in the HR diagram, but close to the main sequence the value of dependence is L is proportional to m cube. Okay, perfect. So we know now the more your massive object is, the luminosity of the star is going to be higher. So if you have more massive star, luminosity of the star would be higher. Remember that we are talking about in the vicinity of main sequence or at the main sequence. Okay, maybe Rohit, can you open the other video? Yes, thank you. Now let's assume that we have a group of stars along the main sequence, and they obey the mass luminosity relation what we have just derived. Okay, so it means for them luminosity is related to m cube, and they also have a relation between radius and their mass, and this radius is almost proportional to their mass. So radius is proportional to m to the power 0.9, close to r radius proportional to m, and this is here in this case we are taking not exactly 1, but r is proportional to m to the power 0.9. Okay. Now the question which is mentioned here is you have to determine the mass dependence of Kelvin-Helmholtz time scale. Do you remember what is Kelvin-Helmholtz time scale? There were three kind of time scales Professor Glassell has already mentioned in one of the previous lectures. So what kind of these time scales were? Dynamical time scales, nuclear time scale, and thermal time. Yes, very good. So thermal time scale, sometimes it is also referred as Kelvin-Helmholtz time scale. So in this question, here it is being asked that you have to determine the mass dependence of Kelvin-Helmholtz or thermal time scale. Okay, and then after that you also have to calculate what is the tau kh, means the Kelvin-Helmholtz time for sun, and if you know for sun, probably what will be for some other stars. Okay, but for the time being, let's stick that we would like to first determine the time dependence, the mass dependence, not the time dependence, mass dependence of our Kelvin-Helmholtz time scale, and then we try to calculate the value of our thermal time scale or Kelvin-Helmholtz time scale for the case of sun. Okay, so how we define Kelvin-Helmholtz time scale? Any idea? Any suggestion? E thermal by luminosity, means the thermal energy content divided by the present luminosity of the star. So it means in a more crude way, you have certain amount of thermal energy, and the star will also have the luminosity, right? So luminosity is basically nothing but how the star is losing energy per unit time. So if you want to define the time scale, Kelvin-Helmholtz time scale or thermal time scale, there is like you compute the thermal energy content of your star and divide it by the luminosity of the star. Okay, that's how we define, or that's how we calculate thermal time scale. So it means the time which is required for a star to lose all its thermal energy. Okay, all the thermal energy, whatever thermal energy star has. Okay, so it means if I want to calculate the thermal time scale or Kelvin-Helmholtz time scale for any given star, then I need to first compute the thermal energy content for that star and divide by the present luminosity or the current luminosity of the given star. Okay, clear? And thermal energy content, how we define the thermal energy content in terms of G, M and R. It's already mentioned there, so you can take a look. Okay, so G M square divided by R. Okay, I should hide it next time. G M square by R, and then you have to also divide the luminosity. Okay, so obviously, what is the unit of this expression? Are we getting the time unit time? Because we are saying that it's time. The dimension of this expression is. So what is the dimension of this quantity? Gm square by R multiplied by or divided by R, L, time. Obviously, you have Gm square by R. So if you assume it's form of energy, and then luminosity. What is the luminosity? Energy per unit time, right? So it means this energy and then divided by energy per unit time. So obviously, the energy will cancel. The unit of energy will cancel, and you are only left with luminosity. The time. Okay, that's fine. Now, considering so what we can say that the Kelvin-Helmholtz time scale or thermal time scale is proportional to m square divided by R into L. Now, from here, can you tell me what will be the mass dependency of Kelvin-Helmholtz time scale for the given star? What we need to do? What we need to do? Mm-hmm. So what we need to do, first of all, what we need to do here, it was already mentioned earlier that we had the luminosity, how the luminosity was related to the mass, and how your radius was related to m. Okay, so the only thing what you need to do is that convert this L into m, convert this R into m. You will immediately know what is the mass dependence of the Kelvin-Helmholtz time scale in this case. What you are getting? What is the value you are getting? Okay, let me see. Can you check whether I am correct or incorrect? It's fine. Okay, that means that the Kelvin-Helmholtz time scale dependency is m to the power minus 1.9, close to m to the power minus 2. So if the mass of the star is more, then what will happen to the Kelvin-Helmholtz time scale? So the question, let me rephrase the question. How the Kelvin-Helmholtz time scale is going to vary for different stars in terms of mass? It's fairly simple from this expression. You increase the mass, that the Kelvin-Helmholtz time scale is going to increase, right? You don't have to even think about it. It's fairly simple. Okay, perfect. So now we know that how the mass, how the mass, how the Kelvin-Helmholtz time scale basically depends on mass. Okay. So now can we calculate it for the case of Sun? So for case of Sun, now you know the value of m, you know the value of r, you know the value of L. So if you substitute the value, let's see if I can. Okay, so now since we are in the problem solving session, so now I invite you to just give me the order. Okay, order of whether it is few years, some billion year, million year, just need an order. 10 to power 7 years. So of the order of 10 million Kelvin. Okay, so perfect. Okay, so yeah, I mean I'm getting 1.6 close to what you were saying into 10 to power like 10 million years or 16 million years. Now, if you know, for example, let's say we now know the value of Kelvin Helmholtz time scale for the case of Sun. If I'll give you any other star, let's say we have another star. The mass of the star is 4 times mass of our Sun. Then what will be the Kelvin Helmholtz time scale? First of all, it is shorter or longer? Answer is obvious. Should be shorter. What will be the order of the time scale? 2000 years. So you already have this for Sun, and you can write for Sun, and then you can write for another star and take the ratio. For example, 1 million year. All of you are getting that time scale. Is closed in terms of in terms of magnitude. So this terms of just order of magnitude. It's million years. 1 million, close to 1 million years, or 10 to the power 6 years. Okay. Okay, it's good. Now you can take another example argument, and you can verify this argument. The argument is that you have to prove that using the mass-luminosity relation, you have to prove that the massive stars, they evolve faster than the low mass stars. The argument is that massive stars, they evolve faster than the low mass stars. Can we prove that somehow? So what is the time scale? The time scale which time scale will be involved here? When I say you have to show that the massive stars evolve faster than the nuclear energy time scale. Okay. Just by the relation, I mean the hint is also mentioned, the mass-luminosity relation. Can you show it from the mass-luminosity relation? How the nuclear time scale will depend upon the mass? We just did it actually. No, you don't have to go in that direction. More mass, more luminosity. You just think about the formalism for nuclear time scale, how we define the nuclear time scale. How we define the nuclear time scale? So in terms of some formula, if you remember anything. Let me just reveal a little bit here. So the nuclear time scale is actually basically is expressed in terms of a fraction, a constant, multiplied by m c square divided by current luminosity of the star. Okay, so we're basically using a mass energy equivalence relation here. So we have a fraction here 0.007 into delta m or m in c square divided by luminosity. Okay, so again you can check the dimension. Obviously this is representing the energy, and you have energy per unit time. So obviously energy is going to cancel. The only thing what you are left is the time. So this right hand side is actually representing the time. Okay, now what I am saying is that you have to prove, or you have to show that the massive stars, they evolve faster than the low mass stars. So how we can do that? Exactly. So now what you do here, you already know what is the dependency of luminosity and mass. So how the luminosity vary as a mass. So this L is proportional to m cube. So for in most of the cases close to main sequence, then if you simply substitute this L proportional to m cube, let's see what we get. Okay, so this is L. I'm just representing this L in case of sun. So in case of sun, let's calculate it. So what you have in case of sun, you replace m by the solar mass, and you just replace L by the solar luminosity. Okay, and if you compute it, you will get a value, a time. And this time, what we get is of the order of. Is it correct? Do we expect that? If yes, why? If not, why? So nuclear time scale is greater than the thermal time scale. That makes sense, right? Here it is greater. So that is fine. That seems in that context, it is fine. But what is wrong in this time scale? On this time scale, 10 to power 11 years. 10 to power 11 years. Exactly. So the time what I mentioned here is like 100 billion years. Okay. So we are getting a time scale which is 10 to power 9 years. For the case of sun, we are saying that the nuclear time scale is of the order of 100 billion years. And what is the time? What is the age of our present universe? Then we have to go back to our calculation, and we have to see what went wrong actually. Do you have any idea? You only consider the hydrogen burning, one argument. Any other argument? We have only considered hydrostatic equilibrium. Any other argument? The point is that for burning of the nuclear reactions, not the entire mass is not available for burning of burning actually. So only a fraction of mass for a particular star will be available for nuclear burning. So in case of a typical star, that mass which is available is around 10%. And here, while performing this calculation, what we have taken here, we have taken the entire star, we have taken the entire sun in order to find out this time scale. Okay, so this is why we are getting an order which is 100 billion years. Okay, so now if I say only 10% material is available for hydrogen burning, for nuclear burning in more general, then what will happen to this number? Now this number will reduce to 10 billion years. Now it appears it's a reasonable value. Okay, a star like our sun can have a lifetime, or the nuclear time scale, or the evolutionary time scale for a star like our sun will be of the order of few billion years. For example, in this case we are getting 10 billion years. Okay, the question what I mean, why only 10% material will be available for burning, nuclear burning? Any basic argument? So we have a star. We have a star, right? A spherically symmetric object. This is the center. Let's start here. We have r is equal to 0, and this is our surface. Okay. Generally, in general, the conditions which is required for nuclear burning is achieved or available within the or inside the core of the star, or vicinity in the vicinity of the center part of the star. Okay. So even though you have a large amount of material here in the outer part, these materials will not have kind of conditions what you need in order to go through hydrogen burning or helium burning or carbon burning or oxygen burning. Okay. So the material which will be present in the vicinity of central part of the star, only these materials is typically available for hydrogen burning. Obviously, the processes like convection can take the materials. For example, they can mix the material which is present in the outer part of the star, but that's a different story. Okay. Typically, approximately 10% mass of the star is available for nuclear burning, and since we considered in this example while calculating the entire evolution time scale for the nuclear time scale for our sun, we have considered the entire mass of the sun. That is why we were getting off by by 10, a factor of 10. Okay, is it clear to all of you? Right? Yes. Yes. You see, most of the star, most of the mass is center is close to the center. But in when you have a star close to the main sequence, or in the vicinity of the main sequence, the the conditions what you require to burn the hydrogen or to burn the helium or other heavier elements will not be available in the other part of the star. Okay, so even though you will have a large fraction or large amount of material will be concentrated in the center, that does not mean that the entire region, entire central region is having sufficient condition for ignition of either hydrogen, helium or other heavier elements. Okay, clear, right? Okay, any other question? Okay, perfect. Yeah, this was the argument already discussed. Yeah. So how you can prove very simple argument, how you can prove the fact that the massive star they evolve faster just by having the knowledge between the having the definition of the nuclear time scale plus relation between mass and luminosity. You don't need anything. It's just very simple argument. Your tau nuclear will basically depends upon the mass divided by L, and L is proportional to m cube. So in this case, your nuclear time scale will be proportional to 1 divided by m square. So it means the more mass it is, the more mass your star will have, the nuclear time scale for that star would be shorter. So it means the more massive your star is, the faster it is going to evolve. Okay, and you know why this is taking place only by knowing the definition of the nuclear time scale and the relation between mass and luminosity. Okay, so that is why you can easily say that the more massive stars they evolve faster than the low mass stars. Yeah, we to the previous content. Ah. So another topic of interest for today is the period density relation. Okay. Now you see, Professor Glasser has already pointed out how the period and density is related. So I'm directly taking the relation from there and just mentioning it here. You can also look at the lecture notes which were provided. How this relation is coming to the picture. Very basic argument, you can derive this relation. Okay. Now, if you have this relation where P here is representing the period, okay, P is standing for the period, and under root rho rho bar is basically representing the mean density, and this period is related to the fundamental period. And if you take the multiplication of this fundamental period with the mean density of the star, that quantity is going to be a constant. Okay. Now, the question here is that if you have two stars, let's say we have star A and star B. Okay, so let's consider that we have two stars, star A and star B. So for star A, the radius is given. Radius of the star A is 12 times the radius of our sun. In stellar physics, many occasions you will find that the mass, radius, luminosity, these quantities are actually expressed or being expressed in terms of solar unit. Okay, so similarly here the radius of the star A is given in terms of solar radius. So R is equal to 12 times the radius of our sun. Okay, so radius of star A is given. Now the fundamental period for star A has been found, and which is 2 days. So the fundamental period of the star A is also mentioned, is also given, and which is 2 days. Okay, so for star A we have the radius and the fundamental period. For star B, the lambda max. Lambda max is basically representing that the maximum, the intensity, the wavelength of associated with the maximum intensity. Okay, so just to remind you, stars, we assume them that they are black body. So in this case, if I plot their intensity or brightness or energy density in terms of wavelength, what you will get a profile which will look something like this. Okay, and this is my lambda max. So the wavelength, particularly wavelength associated with the maximum intensity of the given star. Okay, so which the star is emitting the radiation in all wavelength, and at a particular wavelength or in a range of a particular wavelength, it will be emitting the maximum intensity. Okay, so in this case, lambda max is given to S. What is the lambda max? Is yes, it is already here, 467 nanometer. Okay, that's fine. Now, if the luminosity of a star B is 2340 times luminosity of our sun, then the question is that can we estimate the fundamental period of star B? Okay, so we have two stars, star A and star B. For the case of star A, we already know what is the period and what is the radius for the star, and then for star B we have lambda max. Okay, and then in addition to lambda max, we also have the luminosity of that star. And luminosity of that star is given in terms of solar luminosity, and this is 2340 times the solar luminosity. Okay, do you have any idea how we can compute the period of another star, its period of star B, fundamental period associated with star B? Any idea, any argument, or you need some hint? Some hints required? So we have two stars, star A and star B. For the case of star A, the fundamental period and the radius of that star is given, and for star B we have the wavelength associated with the maximum intensity and we have luminosity of that star, okay, in terms of solar luminosity. So the question is that can we estimate, or how we can estimate the fundamental period of star B? Mm-hmm. 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 Any other idea? What shall we do with lambda max? Why the lambda max is mentioned? Why it is important? So if you have the lambda max, then we can find out the temperature, right? Okay, and once you know the temperature, if you know the temperature, then what we do with the temperature? Yes, luminosity is given, then we can find out the radius by using temperature, luminosity, radius relation, and that relation is known as, no, not mass luminosity relation. Mm-hmm. Okay. So as you know that what I said earlier, we have relation between period and density. Okay. So if we have the relation between period and density, if the period and the density, mean density, the square root of the mean density is equal to constant. If you have two stars, so for these two stars, you can write actually right. Can we write that? And in this case, what we want to figure out what is the value of PB. This is period associated with our star B. Okay, so it means you just simply take this that side. So this PB is simply period associated with star A, and then is rho A divided by rho. Okay, so the entire thing what you have to do is that if you know somehow relation between rho A and rho B divided by rho B, you will be able to find out what is the period of your star B. Okay, can we express this relation in terms of radius? Probably it is also already mentioned here. Okay, I don't have to write it right down here. It's already given. So if you write in terms of radius, so this will become the radius of star B cube divided by radius of star A cube. You can convince yourself by converting density into mass and radius. Remember that for this given example, we have considered the same mass for these two stars, star A and star B. Okay, the both of the stars, star A and star B, they have the same mass, and by knowing that they have the same mass, if you know somehow what is RB and what is RA, immediately you will be knowing what is period of star B. So for the case of star A, we already directly know what is the radius of star A, but our entire task is now to find out what will be the radius of star B. And we already know, you already told me that this is how we find out. So Stefan and the Wien's displacement law, by applying the Wien's displacement law, you have to first figure out what is the temperature, surface temperature of the star. And once you know the surface temperature of the star, then you use the relation which is known as Stefan-Boltzmann relation between luminosity, radius, temperature to figure out what is the radius. If I write down this relation here, We already know T effective or surface temperature because we know lambda max. And if you remember Wien's displacement law, what the Wien's displacement law states, it says basically that lambda max multiplied by your temperature, that will be equal to constant P. Okay, so it means from here you can easily find out what is the surface temperature, and you know the surface temperature and the luminosity. From this relation you can find out what is the radius of star B, and the moment you know the radius of star B, then you know the pulsation period of star B. Okay, the period what we are talking about is a fundamental period. Okay, this is already mentioned. So what we do here, basically we take the first, we find out what is the effective temperature, and then by using the Stefan-Boltzmann relation you can find out what is the radius of the star. Okay, this is what is mentioned here. So anybody, did you find what is the temperature of the star is? Temperature of the star B is surface temperature. The value of B is already mentioned here. B is equal to 2.9 into 10 to the power minus 3 meter Kelvin. You only have to just multiply two numbers actually. .2 kilokelvin or 6200 Kelvin. Okay. Okay, this is the value what I'm also getting. T is equal to 6200 Kelvin. Okay, so now if you substitute the value here, obviously you will get the period associated with star B. Okay, star B is equal to, I mean the period of star B is given in terms of period of star A, and then the ratio of radius of star B and the radius of star A, the cube is also taken into account. Clear? So it is your task to find out what is the period of star, and you tell me later on what will be the period of the stars. Any doubt? Anything on this question? Very straightforward questions. Okay, perfect. Now, the next content is a very interesting theorem, and we will be using, Professor Glassell will be telling us the use of the Virial theorem and the wide application of Virial theorem in stellar astrophysics. Here we will try to see how we can prove the Virial theorem actually. Okay, and there are different ways we can prove it obviously, and this is one of the ways what we are going to do it here. I suggest you to also try the other ways by which we can prove the Virial theorem. Okay, so we'll come back to the statement of the theorem, but we'll try to consider first in our context how we can show the equations or the relation between certain quantities, and we try to state back what is the Virial theorem. So if you consider a star, and the star is a kind of bound spherical gas system with a particular mass m, and it is in hydrostatic equilibrium. So in this case the mass conservation can be written in this equation, dm by dr is equal to 4 pi r square rho. Okay, so what we are doing basically, we are considering a bound spherical gas system which is the hydrostatic equilibrium. Now you can write this dr is, then if you want to write, sometimes this relation can also be used to convert dm to dr or dr to dm. So if you want to convert dr sometimes, then dr will be equal to 1 divided by 4 pi r square rho. So dr and dm, they are basically connected by a factor 1 divided by 4 pi square rho. Now as I stated, since we are talking about the hydrostatic equilibrium configuration, so in this case the pressure gradient will be balanced by minus gm rho divided by r square, the hydrostatic equilibrium, the standard hydrostatic equilibrium, which is written here take considering r as an independent variable. You can also use, this is known as the Eulerian form, and you can also write taking m as an independent coordinate, or we can write it in the Lagrangian form. Now, if you want to write in the Lagrangian form, then what you need to do is, for example, you have to convert, or you have to express it in terms of dm. So this dr, you can write dr in terms of dm, then the factor 1 divided by 4 pi r square rho will come into the picture. So dp would be dp divided by 1 divided by 4 pi r square rho, dm will come into the picture. This will be equal to the right hand side, which I have mentioned here. Okay. So now if you just see this 4 pi r square, and we also have here r square, since it is 1 divided by 4 pi r square, this will become, this is going to be r to the power 4, and you have a 4 pi factor over here, and the density term is going to cancel each other because this is going up, you already have one density over here. So basically dp by dm is equal to minus gm divided by 4 pi r to the power 4. This equation you have already seen. So here the hydrostatic equilibrium equation has been written in terms of mass as an independent coordinate. Now if you take this expression and multiply 4 pi r cube and integrate this expression over the entire mass range from 0 to capital M, let's say, then what we get? So what we are doing here, basically we are taking this expression, the hydrostatic equilibrium expression, and multiplying it by a factor 4 pi r square. That's 4 pi is, you know, already r is representing the radius. If you multiply this 4 pi r cube factor in this expression, what you will get after integrating from 0 to capital M. Okay. So what I have done here in this expression, you can also try by yourself. You multiply 4 pi r square here and integrate the entire expression from 0 to capital M. So dp by dm, and this multiplication factor 4 pi r cube dm is equal to minus integrating it from center up to the surface of the star having capital mass capital M, gm divided by 4 pi r to the power 4 multiplied by 4 pi r cube dm. Okay. Obviously this capital M and this M is little bit different. So yeah, just trying to make sure that this we are integrating from 0 to this capital M, this one. Okay, which is representing the mass of the entire considered star. Now if you simplify here, for example, if you look at the left hand side, you take out the constants. In this case we have 4 pi, you take out 4 pi outside, and then you write just r cube in front of the in front, and then dp by dm the other side. So what you will be left with, what you will have basically 4 pi and then integration from 0 to capital M, r cube dp by dm and then dm. This will be equal to, you see here what is going to happen, 4 pi they are going to cancel each other, r cube r to the power 4, we are only left with 1 r. Okay, let's park this equation here and we give a name to this tensor, this name to this equation star equation. Okay, we used later on. Okay, so now here what you have kind of two function here, and if you want to perform the integration of two function, what we need to do, we will need to perform the integration by using the formula integration by parts. Okay, and since this dp by dm is a kind of, you know, derivative of p with respect to m, so the integration of parts formula in the cases where you have two functions u and then u dash is representing basically derivative of the function u. In these cases the integration of by parts will be is given by u multiplied by v minus and then integration u dash is representing the differentiation of u with respect to the considered variable multiplied by v, and then you have dx. Okay, so what we need to do, we need to just take the same the integration by parts formula and apply on the left hand side of this expression, left hand side of our equation star. Okay, if you do that, okay, so I'm just writing here left hand side. So basically what you have it here. Obviously now the question would be that which one we should consider u and which one we should consider v dash. Obviously we can conveniently consider dp by dm as a v dash, and we consider u r cube as a u. So considering u as r cube and v as p, what you will end up getting is the first expression here would be just u into v, and v would be p, right? V would be p, and then obviously you have to also take the limit from 0 to capital M. So this is 4 pi, and inside the bracket but you have r cube, this is our u, and you have p, which is actually v. Okay, so this quantity what you will get at the end here. And here what you have, you had actually r cube, and if you differentiate it with respect to m, so r cube, if you differentiate it, what you will get actually 3r square and then dr by dm. Okay, then obviously the other quantity is p here and p and dm. Now let's focus on this expression here. What will be the value of this expression? It will have some value or it will vanish? If it will vanish, what is the argument why it will vanish? It will vanish for obvious reason. At the center where your mass is equal to 0, which quantity will be 0? R will be 0, and at the surface the pressure, we can assume that the pressure is approximately 0. Okay, pressure is not exactly 0 at the surface of the star, but compared to the internal or compared to the center of the star, the pressure is almost negligible. Okay, so in this case, when you are considering the limit 0, so it means at the center radius will be 0 and at the surface pressure will be 0. So it means this term, you can forget about this term actually. So this term is going to vanish because of the property of our configuration. Okay, what about this term? So we are left with this term here, this one. So we have to focus on this term. Yes, this is what it is mentioned here. This is 0, and now we have minus 4 pi and the integration. This is the integration. Okay, now what you can also do, you can take the dr by dm relation. This dr by dm is equal to 1 divided by 4 pi r square rho. So you just replace dr by dm by this expression over here. Okay, so dr by dm can be replaced by 1 divided by 4 pi r square rho. This is what you will get at the end here. So I am just replacing this quantity dr by dm here by 1 divided by 4 pi r square rho. This is why I told you that we'll use to convert from dr or to go back from dr to dm, or we sometimes use to get rid of dr by dm. Okay, this relation. Now if I simply write this expression 1 divided by 4 pi r square rho, then you see p into dm. This r square is going to cancel each other, and what you have here, for example, if you also have 4 pi which is outside of this integration, and you also have 4 pi over here, so this 4 pi and this 4 pi, they are also going to cancel each other. Then you will be left with 3, and then integration from 0 to m, you have here p divided by rho dm. Do we all agree with that? This is okay? Okay, perfect. Now substituting this expression into our equation star. So we have considered the star equation and the left side of the star equation. So the left side of the star equation is this quantity actually. So we will put this value in the left hand side for star equation, and this is what you will get actually. Okay, minus 3, and you have integration from 0 to capital M, p divided by rho dm is equal to minus integration from 0 to capital M gm by r dm. Okay, let's call it double star equation. Okay, now if you look at the left hand side and right hand side, can you assume or can you guess what kind of quantities we are dealing with at the moment? Okay. So for a perfect monatomic gas, the internal energy per unit mass is typically given in the form of E is equal to 3 by 2 P divided by rho. Okay. So if you look at the left hand side of this expression here, so it is a form of our internal energy per unit mass. This is the expression, typical expression for a perfect monatomic gas. The internal energy per unit mass is given by a factor 3 by 2 multiplied by pressure divided by density. Okay. And the total gravitational potential energy for the system, for example, you consider a system which has a mass capital M, that is typically given by, let's say that this energy is represented by Greek letter omega. This omega would be equal to minus and the integration from 0 to capital M Gm divided by R dm. Okay. So we are trying to find out what are the quantities which are involved in our equation double star equation. Okay. So the left hand side is kind of, we are dealing with internal energy, and right hand side we have the form of gravitational potential energy. Okay. Now if you substitute these two expression, actually if you look at this star equation and you substitute the value of E, means the internal energy per unit mass, and the gravitational potential energy of the system, in this case you will end up getting a relation between E and omega. Okay, remember that E is representing the internal energy and omega is representing the gravitational energy here. So E will be equal to minus omega by 2. Okay, and this is the very famous statement of the Virial theorem. Can anyone state what it is? I mean the internal energy, how the internal energy in a gaseous object which is in hydrostatic equilibrium is connected. So the internal energy and the gravitational potential energy, they are connected. E is equal to minus omega divided by 2. Okay, let's take this relation. Obviously when we talk about the total energy of the system, in this case the total energy would be the summation of your E and your omega. If you add them together, you will get the total energy of the system. So let's add them together and you see what we get. If I can write here, for example, omega in terms of E, so omega in terms of E would be minus 2E. Okay, if I replace here, the total energy would be the sum of E and omega. So if I replace omega in terms of minus 2E, what will happen to the total energy? Total energy of our system, in this case we are considering a star, total energy would be equal to minus E, or total energy is equal to minus omega by 2. Plus omega by 2 or omega by 2. Okay. So the total energy of the system is negative. What does that mean? System is bound. Okay. So whenever we have the total energy, which total energy is negative, we say that the system is actually bound. So for bound system, what is the characteristic of bound system? If you think in terms of internal energy and the potential energy, typically the content is basically the potential energy is much higher in terms of magnitude compared to the internal energy of the system. Okay, that's why it will at the end, if you try to add them together, the content is so high that the total energy will be negative. Okay, do you know what is the sufficient, not sufficient, maybe necessary condition for an object to be bound? Any idea? Master students particularly, what is a necessary condition for a system to be bound? What should be the nature of the forces which is holding the particle? The overall forces which is holding the material, that should be attractive in nature. Okay, so this is a kind of necessary condition to have the system bound. Otherwise, if there are repulsive forces, obviously you will not get the bound system. Okay, so we end up having a expression for the total energy, and the total energy is basically a negative, and this total negative energy indicating that we are dealing with a bound system. Okay, it's fine. Now the luminosity can be written. How we can write the luminosity? If you have the total energy, what we said, remember that. What is the definition of the luminosity? Energy per unit time. So the energy rate by which the star is liberating the energy, right? The rate by which the star is actually losing the energy. So it is like if you have the total energy, you differentiate it with respect to time, the quantity what you will get is a kind of luminosity. Okay, so if you have E total, and if I simply take the time derivative of E total, that is going to give me the luminosity. Or luminosity would be how your total energy is changing with respect to time actually, or per unit time. So L would be equal. So if I would like to write the luminosity in terms of E total, in terms of total energy, so luminosity would be equal to minus of the E total divided by dt. Okay, so or differentiation of E total with respect to time t. Now you can write from here this E total, since E total is equal to minus E total is equal to omega divided by 2. So in this case, luminosity L would be equal to minus 1/2 of d omega by dt. That's how we can write the luminosity. Okay. Now, can we have negative luminosity? So right hand side is negative. We can have negative luminosity. Someone is saying yes. So if I want to get a positive luminosity, what should happen to here, to this expression? Anyway, probably the argument is already mentioned here. Okay. So I have already revealed the argument, but the point is that omega has to decrease in order to produce the positive luminosity. You see the expression here. Okay. So in order to have the positive luminosity, the omega has to decrease. What does that mean? The star has to contract in that situation if you would like to have this positive luminosity. You can state in that way as well. So yeah, I mean at the same time, if you look at the internal energy, so internal energy will increase by an amount which will be, let's say, delta E. Delta E would be equal to minus delta of E total, and this will be nothing but minus of delta omega divided by 2. Okay. So what will happen? The star will heats up when the energy is lost from the surface. Now, I don't know whether you have heard about the idea of negative heat capacity. Okay, if you have a cup of tea, for example, I place it here. What will happen to the cup of tea? The energy content, if it is releasing certain amount of energy, what will happen to the temperature of the cup of tea? The temperature will decrease eventually, right? And the cup of tea will attain a temperature which is equivalent to the room temperature. Let's say if the room temperature is 27 degrees Celsius, so obviously in this case your cup of tea at the end will also have the same temperature. Is it possible that the cup of tea is actually losing the energy, at the same time it is also increasing the temperature? If yes, I mean, first of all, do we have that situation? Question number 1. And second, if yes, what is very special about that cup of tea? Think about it. So, what is the difference between, for example, if you have an object and I say I have positive heat capacity, and then I say that I have a negative heat capacity? What does that mean? Yes. Okay. So the negative heat capacity means even though you are taking out certain amount of energy from the system, still you are having, the temperature of the star, temperature of the object is actually increasing, right? So in these cases, what we will see at the end in these cases, that the star will heats up. So for example, this delta V, delta E eventually is equal to minus delta omega divided by 2, and if this is negative, so eventually what you will have a positive value here. So in this case delta E will also have certain positive value. So it means the energy content or the internal energy is also increasing actually. So in these cases what will happen, you have a luminosity of the star, at the same time your internal energy of the star is also increasing. That is why it is said that the star has a negative heat capacity, okay, because it is losing the energy, at the same time the internal temperature of the star is, or the internal energy of the star is increasing actually, okay. So it is losing the energy, at the same time the internal temperature of the star is also increasing, okay. So generally what happens, or the very famous way of arguing, or one of the way is saying that whenever actually when you look at many standard textbook, or when we study in the school levels, most of the time it is taught that the main source, or the primary source, or the only source of energy in the star is the nuclear energy, right? So if it means that if the star is not having nuclear reactions, probably you will not have the luminosity, okay. So maybe I'm not going too much into that direction, because Professor Glaser will be also talking about that aspect to answer your previous question, answer the previous pointed question, that how the how the stars shine, okay. But the point here is that from the contraction point of view, when the star will contract, it will use the gained gravitational potential energy to maintain its luminosity and to heat itself, okay. So half of the gravitational potential energy will go into maintaining the luminosity of the star, and the remaining half basically will be increasing the temperature of the star, or basically it will be kind of contributing more into the internal energy of the star. So half of the energy will be radiated away, and remaining half of the energy will increase the internal temperature, or you can say the internal energy of the star, okay. That is why it is said that the star has negative heat capacity, okay. Now where or in what evolutionary phases the star actually contracts, stars they contract and they use the gravitational potential energy, or the form of the gravitational potential energy, to maintain the luminosity and increase the temperature. So this is the HR diagram. I'm just plotting here in a conventional way. On the x-axis you have the surface temperature of the star, and on the y-axis you have the luminosity of the star. So surface temperature by convention is increasing in the negative x direction or increasing in this direction. So whenever you see the HR diagram, the surface temperature of the star is actually increasing. On surface temperature is being represented in this diagram on the x-axis, and the is increasing in that direction, okay. Now the luminosity is increasing in the positive y direction, that is fine, and generally you see the luminosity is given in terms of logarithmic of L divided by L naught. What is L naught? Solar luminosity. So you take the luminosity of the star divided by the solar luminosity and take the logarithmic value of this one, okay. So in this case, what will be this value for sun? 0, right? Good. So now you see here what I am representing here in the HR diagram, the Hertzsprung-Russell diagram. We are representing a location of so-called main sequence. What is the main sequence? Professor Glassell has already today given you a brief overview about the stellar evolution, how stars evolve. So when they start burning, when they have sufficient condition after the formation, when they have sufficient condition, they basically start burning hydrogen at the center. And when they generally start burning hydrogen at the center, the location in the HR diagram is, if you plot or if you try to put many stars in this diagram, for example, you have, let's say, several thousands of stars, you will find that in a particular group of stars, for example in star clusters, most of the stars they will lie in a sequence or in a particular region of the HR diagram. We call this region as a main sequence. And what is the condition for a star to be main sequence? The criteria of the star to be on the main sequence is that the star is burning hydrogen inside. So the main nuclear reaction is basically the hydrogen burning. Okay. Now, after obviously how the star is going to evolve from the main sequence. So from the main sequence, it is going to evolve towards the so-called sub-giant branch phase, red giant branch phase, and so on. What will happen in the previous example? What we have seen that obviously not all the material will be available for the hydrogen burning. So at one time, a star will go through a phase when it will run out of hydrogen at the center. Okay, when it will run out of hydrogen at the center, because remember, we have this spherical symmetric gaseous object. This is the center, r is equal to 0, and we have r surface. Now what you will have certain region inside the star where you will be having some sufficient condition to burn the hydrogen into helium, right? But what will happen at one point, the hydrogen fraction in the vicinity of your center or in the core will actually reduce as time. The fraction, for example, if you started with 70% of hydrogen at the center, so this is a typical configuration in sun-like stars. You have 70% hydrogen, you have around 28% helium, okay, and you have approximately 2% other heavier elements. Okay, we call them collectively metals. Okay, in stellar astrophysics, so to all my undergraduate students who are attending first time kind of the stellar astrophysics courses, so for them I would like to emphasize that hydrogen, helium, and rest of the elements we call them as a metals or heavy elements. Okay, collectively call them heavy elements or metals. Okay, in case of sun or sun-like stars, the chemical composition is like you have approximately 70% hydrogen, you have 28% helium, and around 2% metals, means all the other heavier elements apart from hydrogen and helium. Okay, so obviously when you start at the main sequence, or when this star is going to start the hydrogen burning at the center, you start with a chemically homogeneous system, right? And as the time will pass, what will happen at the center or here, the hydrogen will be converted into helium. So obviously one time will come when your entire hydrogen or a substantial portion of hydrogen in the vicinity of core has been converted into helium. Okay, so obviously what will happen, you do not have more hydrogen for burning actually, and if the condition is not satisfied for helium burning, because you need more extreme condition for helium burning, these cases what is going to happen, your star will try to somehow maintain the luminosity and try to heat it itself. And how it can do that? By contracting. Okay, now in the HR diagram, this is the location of main sequence. At this point, star has started burning hydrogen. Now as it is moving towards this, from this location, obviously sometimes this entire region we call it as the main sequence until the point where you have hydrogen burning here, and this is maybe considered as the zero age main sequence, location of the point in the main sequence where the star has just started the nuclear burning. Okay, so at this point, if you call it as a zero age main sequence, obviously at one point when the star is evolving, at one point what you will have, you will run out of hydrogen in the center. Okay, most of the hydrogen is being converted into helium, and now the condition, means temperature, density, what is required for helium burning is not sufficient enough to ignite the helium. Then what the star is going to do, it's going to shrink slightly. When it is going to shrink, what is going to happen, it's going to heat itself and maintain its luminosity by using the idea of Virial theorem. Okay, so this is the point A. It will reaches point A, it will go into the phase so called overall contraction phase. The star will slightly contract itself. Okay, it will reach to the point B, and at this point B, it will have sufficient temperature to burn or ignite burning in the shell around the nucleus. Okay, so from here onwards, it will start proceeding towards the red giant branch phase. Okay, so the point is that in the overall contraction phase, the star has, what it does is basically contracts, and with this contraction, what you can have the you can gain the gravitational potential energy, and half of this gravitational potential energy can be utilized to maintain the luminosity of the star, and the remaining half can be used to heat itself. Okay. Okay, perfect. So maybe I invite Professor Glassell if you would like to make any comment or anything on the. Okay, I see. Any question from your end? Yes. Yeah, so you can see this relation actually. So you can also just look at this. I mean, for example, what he was trying to say here is the relation between E and omega. Okay, so E total is 1/2, or this is how this is related. The relation between E and omega is related by a factor 1/2 actually. So that is the argument why we are saying it. Yes, why. So this is very interesting actually, and whenever people said that the star is only, or a star can only get the source only from the nuclear reactions, probably you should immediately object, and you should also say that there are other possibilities. Star can also maintain its luminosity, or it can also heat itself by using some other source of energy. Okay. So again, do you have time? Or any other question at this point? The another topic which I would like to briefly mention here is the role of pulsating stars in distance determination. Okay. Do you have any idea how we use these stars, pulsating stars, in distance determination? You thought about it, or any idea? The title of our Gyan course is stellar pulsation, right? And the application of stellar pulsation. We ask ourselves why we should study the pulsation of star. The very fundamental question, right? And if you are convinced that why we should study the pulsation of stars, you feel a bit more motivated to study the pulsation of stars. One of the one of the very fundamental application of pulsating star is distance determination, or probing the distances. Why it is important for us to know the distances? If there is a star very far from us, so why it is important to know the distance, how far it is? What is the argument why we should know? Expansion rate of the universe. Any other argument why we should know the distance uh, from here to star? To find out the luminosity, to find out the intrinsic brightness of the star. Okay, if you don't know what is the distance, you only measure the flux, right? And if you only have the information about the flux, it will be really difficult to know what is the intrinsic brightness, or you say the luminosity. Okay, luminosity of the star. So obviously one of the very wide application of distance determination is that once you know the distances, you can figure out the luminosity of the star. What is the intrinsic luminosity of, or what is the luminosity of the star, not intrinsic brightness of the star is actually. And if you see the HR diagram, we are very much interested into the surface temperature, into the luminosity of the star. And in most of the cases, when we study the theoretical aspect of stellar physics, we generally deal with the luminosity of the star, because luminosity is something which is intrinsically related to your object. It has nothing to do with the distance actually. So we eliminate any distance, because as an astronomer, you measure the flux and then you try to figure out what is the luminosity. And once you have the luminosity, we know this is the intrinsic brightness, or this is the intrinsic property of the star, and then you can study the stars by knowing the intrinsic property, luminosity of the star. Okay, so now I invite you to tell me your thought how we can your idea is how we can use the pulsation to find out the distances, particularly master students, how we use Cepheid variables. Yes, so we have a period, so-called period luminosity relation. What is that relation? Anybody is interested to tell me what is that relation? Period luminosity relation. How it should be connected? How the period and luminosity should be connected to each other? I'm not going into the details. I'm just saying what is the argument for distance determination. The basic idea is that these Cepheid variables, they are very special class of variables and the luminosity. Okay, and they have a very. It means that, for example, typical relation. I'm just telling you how it is used actually. So the higher is the period, the more that's the relation kind of period luminosity star period luminosity relation between the classical Cepheids or typical Cepheid variable. If I can measure the period of a star, and I already know empirically from observation, I already know the relation between period and luminosity. I'll be knowing what is the luminosity. Is it easy to find out the luminosity, or it is easy to find out the period? Because yeah, because it is very easy when you have an object which is very far and you're only bothered about the fact that to time. Okay, does not matter how far it is, how close it is. If you are able to measure certain number of photos, these are the changes what you see. So you can find out the period of that star. Okay, so in case of very special class of the period and luminosity is tightly correlated. It means we have a empirical relation between period and luminosity of the star. So if you tell me this is the period what I, and once I tell you what is the luminosity of the star is, then can you find out the distance? Yes, so you know what should be the distance, right? So all those special class of variable stars where we have a very tight correlation between variables, by knowing the pulsation period, by knowing their period, we can find out what will be their luminosity. And if I'm just taking a random value, probably it is not related to any star, just taking a random value, let's say relation which is valid for my Cepheid class of Cepheid variable stars. So if that relation is valid for Cepheids, which is having a period of maybe, for example, let's say maybe 12 days, okay, correspond certain luminosity, and I know the value of my luminosity. Okay, if I or intrinsic brightness or luminosity of the star is, by knowing the flux we can measure from the telescope, from on the detectors. So if you know the luminosity, you know the flux, you can find out what is the D or what is R. Okay, so that is the very useful application of pulsation of stars, but it has certain limitations. Remember that. First of all, your variable star means your pulsating star must have this tight correlation between luminosity. Okay, if you have certain uncertainty in that aspects, then obviously if because if there is any kind of uncertainty, but we have certain Cepheid variables or certain class of tight correlation are basically very useful to find out the distances. Okay, and once you know the distances, obviously then you can also if you can also find out many. What will be the flux if you're designing a detector or designing a telescope? You can also think about that. Okay. Okay. Question from your end? I encourage first year students, if you have any question, or students who are having some interesting question. I mean, you do not have the astronomy background and some of the content what we are presenting here is difficult to digest, you can contact us and or you can ask the questions. Anyway, Professor Glassel is encouraging all of you to ask many questions. Okay. Yes. So this is what I said. I mean, the idea is the main statement of the Virial theorem, or the main aspect of Virial theorem, is that the star is having the negative heat capacity, and the negative heat capacity means that even though you are taking out energy from the system, your temperature is actually increasing. Okay, so you're taking out the energy from the system, still your system is heating up. Okay, that is the basic idea. I mean, on Earth it is difficult to see such kind of objects. Our intuition is that you have an object, you have any system, and if you take out the energy from the system, then we expect that the temperature of the star or the internal heat of the star of that object must decrease. Okay, or the temperature of that object must decrease. But at least I don't know, maybe we have any object. I don't have any object in my mind which has negative heat capacity on Earth. Okay, I'm not sure. Okay, so but typical our intuition is that if you take out heat content from any object, obviously that the internal energy and the temperature of that object is going to decrease. But if you have the negative heat capacity, this is what the argument is. The negative heat capacity, it means even though the star is losing certain amount of energy per unit time, because that's how it is maintaining the luminosity. Otherwise, the moment it stops burning hydrogen, if the entire luminosity is only or if the entire energy can only be maintained by the nuclear reactions, and you have no nuclear reactions at the center of the star should not shine actually. After some time, after losing the certain thermal content, it has to stop radiating, right? Because there's no other way. But we know that there's another way the star can maintain its luminosity, and it heats up, and it will heat up. It will continue to contract till the point where your conditions inside the star or close to the core is high enough or sufficient enough either for shell burning, let's say, or for the burning of next nuclear reaction or next level of nuclear reactions. For maybe this can be helium burning or carbon burning, nitrogen burning, or carbon burning, oxygen burning, and other heavier elements burning actually. Okay.